Okay, so let's make a start. So this week, we're going to spend the first hour of this week looking at smart pointers, which are C++11 construct. This continues on from last week, whereabouts last week we looked at what goes into the design of smart pointers and how we can do decent memory management. And then the second part of today, and then for next week and a half, actually, we're going to be spending a lot of time looking at templates and class templates. Now, before I begin, there's a couple of things I wanted to point out. Firstly, what we're about to crack into is a lot of C++11 code, and the textbook that you guys have got is updated for C++11, but it's not strictly the best reference for doing so. I have a second book that I'd recommend to you guys called Professional C++. It's got a lot of explanation of what the C++11 features are and how they work in it. It's not a beginner's textbook, it's an advanced textbook, but if you want to take a look at it, you're welcome to. I picked this up from Dimmicks for about $70. I'm assuming you can get a similar sort of price, maybe online a little bit cheaper. The second thing I wanted to show you is on the right-hand screen here, I have a website up called cppreference.com. You might have already taken a look at it before, but if you're confused about any of the concepts or the library functions that we're looking at, go take a look at this. It will tell you a bit of a description, but the best thing about the site is if you go down to the bottom of it, often it gives you short, small examples of how these things work. Now, if you click the Run This Code button on this website, it allows you to select your compiler and the version you've got, allows you to run it and compile it. And this is important because a lot of people are having issues still with Assignment 2. And the problems that they're sometimes having with Assignment 2 is whereabouts the compiler you've got isn't compiling correctly. You actually might have that same problem with this week's tutorial. We found that if you've still got GCC 4.8, this week's tutorial doesn't compile. It does compile fine under 4.9. But if you've got a problem and you're not sure if it's your problem or if it's your compiler's problem, and you don't know how to install a new compiler, come along to this website, edit the code here. You can change this to whatever you like. Select the version of the compiler you want, and then hit Run, and it will compile against that particular version and show you what the output is. And if it's got an error, it will give you the error. So cppreference.com is a real decent site for being able to see, first of all, the documentation of how things work, but in small examples, and then also to be able to check your code against different compilers. Okay, so let's recap on where we were, or where we are. So last week we looked at the idea of named and unnamed objects. We looked at object lifetimes. We looked at stack unwinding and the concept of exception handling. We looked at new and delete in terms of creating and deleting unnamed objects on the heap. We looked at the concept of resource allocation as initialization and object ownership. And we looked at, particularly on Thursday, the concepts of how you go off and build a smart pointer. And one of the things that we looked at in particular was the idea of reference counting, keeping track of how many things have a reference or have ownership over a particular object, and using that to know when to delete or not delete an object. Now, the reason why I've highlighted new and delete and smart pointer concepts is this is what we're going to continue on for the first hour today. So one of the questions that got asked at the start of last week was, why should we use new rather than malloc? Or what happens if we mix malloc and new, or free and delete? Why would we mix these things up? Well, new does more than what malloc just does. Malloc just allocates a raw block of memory, and then we have to typecast inside it. What new does is new, first of all, creates that empty block of memory, and then correctly creates the type of object that we want to store in that block of memory, and returns, of course, a reference to that object that's being correctly constructed. If anything goes wrong during that construction phase, what happens if the object gets correctly deleted and some sort of exception gets thrown? So new does a lot more things than what malloc does, and it's basically type safe. It's making sure that it behaves exactly as what you expect it to do. And so if something goes wrong, say in the construction of an object, there will be no memory leak because it will be cleaned up. The same applies for delete. Okay? So in C, you had free, which just goes out there and frees the memory. Delete, step 1, goes and destructs the object. It calls its destructor. If your destructor goes and cleans up other pieces of memory, it will do that correctly. Of course, free isn't going to do that. And then the second part of delete is it then frees the memory after it's been cleaned up. And remember that we cannot throw an exception out of a destructor, because a destructor is designed to delete things to clean up stuff. You cannot have an exception leave a destructor, because basically that would result in some sort of memory leak. And so if a exception leaves a destructor, then your program terminates. Also note that deleting a null pointer is safe, because delete is set up to realize how you're trying to delete a null pointer, and it just goes, oh, yeah, it's fine, just lets you do it, and nothing happens. And so we also talked about the idea that after you've deleted something, you should set the reference to null, so you don't end up with a double free problem. That's whereabouts you've deleted the same object twice. Okay, so that's whereabouts we're up to. So C++11 introduces a series of smart pointers. And it's to save us the grief of having to go and write our own smart pointer classes. So all of the stuff we did on Thursday, all those concepts, the important concepts to know, but you don't have to go and build your own smart pointer classes. Use the ones that are available in C++11. There's 3 types. There's a thing called unique pointer, there's a thing called a shared pointer, there's a thing called a weak pointer. And we're going to work through each of these 3 things. But the important things to remember about the concepts is these smart pointers give us automatic management and ownership over unnamed objects. And this means that there's fewer bugs, because you can still end up with double free problems, but there's fewer double free problems. There's fewer problems of dangling pointers. They're exception safe, so if exceptions are thrown, there's automatic memory deallocation, or reference counting will decrease if something gets thrown. And because of reference counting, we have the basis of a garbage collection. Okay? C++11 does not have a garbage collector, unlike Java. Java has a garbage collector. It automatically cleans up memory for you. C++11 does not have a garbage collector, but with the shared pointers and the smart pointers, you can work towards those concepts. And there's also efficiency in the smart pointers. There's a thing called copy on write. We might talk about that in about week 11 or week 12 if we have time, but just know, again, that basically whatever the guys in the STL and the standard template library are doing is probably smarter and faster than what you can do yourself. Okay? So use the C++11 smart pointers. And this week's tutorial goes into a lot of details about the different types and when you'd use the different types. But let's start with looking at the idea of the unique pointer. Okay. And a unique pointer owns the object to which it points to. There can only be one owner. Okay? When the unique pointer goes out of scope, its internal object pointed to by its internal pointer is destroyed. So let's back up a whole lot. The reason why you might use pointers to share around an object. You pass by reference, or if you're back in C, you pass by pointer. And you might have one object, but the problem that we've got is knowing who owns that object. And if we're going to delete that object, which one of these pointers that might all point off to the same object, which one of these things deletes it? Well, with a unique pointer, there can only be one pointer pointing to that piece of memory, and it's unique. So you can't pass it by value. You can pass it by reference, but that's a bad idea, and the tutorials might explain why. Okay? And so when you want to pass this unique pointer around, you have to move it. You have to move and transfer the ownership of it. And so there's an example of how you might do this here. We were talking about the UB stack class a few weeks ago, okay, this bounded stack, or this unbounded stack. What we do is we create this unique pointer wrapper around the call to new. Okay, so C++11, you create a new UB stack, but you pass it into this unique pointer constructor. Note that if you're using C++14, which we're not, but if you were using C++14, you can call this makeUnique function, which wraps that new a little bit cleaner. Once we have wrapped this ubstack object, this unnamed ubstack object, into unique pointer, we can then use the pointer like we'd use any other pointer. And so we can push to it, we can pull from it, and so on and so forth. When it goes out of scope, it's automatically deleted. Now, in terms of transferring ownership, you create a new pointer like that, so there's new pointer P. We can't create a second unique pointer and call the copy constructor on the unique pointer. Because to call the copy constructor would be to assume that we can copy that pointer but still reference the same piece of memory. You can't because it's unique. We can create a second unique pointer, Q2, and not assign it to anything, therefore it's a null pointer. But then we can't say Q2 is equal to P. Again, like with copy, there's no copy assignment. Okay? So what we could do is we could then create Q3, it's still a null pointer. And then what we can do is we can do a reset and this release. So p.release releases the ownership of this unique pointer. You could also use standard move. And q3.reset, first of all, the reset command deletes or calls the destructor on the thing it contains. And then it gets reset to the pointer which it's being passed in. Okay, so unique pointers point to unique objects. You cannot copy them, but you can move them. Okay? And again, this week's tutorial is an example of that. Who's read this week's tutorial, by the way? How many people take a look at it? Okay? My advice is take a look at it because there's a lot to go through. I don't care if you don't understand all the code before you get to the tutorial, but you should have the concepts and the ideas. Particularly this week's tutorial, in the instance of unique pointers, we're looking at the idea of a school, and maybe a school has some lockers. And we allocate or give ownership of a locker to somebody. They take that exclusive ownership over that locker object. Okay? And so that's the idea you might be looking at. I had a question over there. Yep.
Does P get deleted when it's called release?
Pardon?
Does P get deleted when it's called release?
Does P get deleted when you call delete on?
When you call release on line 6?
On line 6, yeah, P.
Or is it just
No, it doesn't delete it. P.release doesn't delete it. It will probably call the move constructor. Again, it's probably a good thing to take a look at the CPP reference. So just do a Google search for standard unique pointer. There it is, top result on Google. And you take a look at release down here. Okay. So release, okay, doesn't take anything in. It returns a pointer to the managed object or the null pointer if there was anything worth managing. Okay? And does it delete it? No, it doesn't delete it. Basically, it just transfers the ownership over. Okay? So release transfers ownership. This is what I was saying before. We've actually got p.release here. You could replace that with standard move. And a similar sort of ability or functionality would occur at that point. In terms of thinking about that, again, this week's tutorial will look at how we shift for ownership of these locker objects across. Okay? So there's a lot to take in. This week's tutorial, I can't stress how important it is. We're leading towards assignment 3, which assignment 3 you'll be doing quite a bit of this stuff. Probably not so much with unique pointers, but with shared pointers, which we're going to get onto in a few slides' time. Now, there's one extra bit to do with unique pointer, though, which I need to explain. So we just said we can't transfer the ownership. So we can transfer ownership, but we can't copy for ownership. Okay? There's one exception to that rule, which is when you're returning a unique pointer. So if I create a unique pointer as a local variable inside this function foo here, and I push some data up onto it, if I return that thing as a unique pointer, remember this thing's about to get destroyed, so the compiler works it out and it transfers of ownership. Okay? So if the compiler's smart, it works out that that thing is going to lose its ownership anyway, so it transfers ownership across. Okay? Again, play with some of this code as you go and take a look at for references. And again, maybe take a look at the textbook or other resources that are available. So let's take a look at unique pointers and exceptions. So I'm going to start down the bottom of the slide, actually. So last week we had a look at dumb pointers, and so a dumb pointer or raw pointer, you just say ubstack star p, okay, it's a pointer, equals new ubstack. Okay, for pointer is the named object, for ubstack is for unnamed object. If there was code in here through an exception, p wouldn't get deleted. Because remember, if we throw an exception at that point and it goes out, stack gets unwound, the pointer gets deleted, but for unnamed object that it's pointing to doesn't get deleted. Okay, so we've got a memory leak. With the smart pointer up here, okay, so we're going to the top of the slide, unique pointer at this point. We don't have any delete unique pointer. If we have any code that throws an exception, that's fine, because this unique pointer object has ownership over the unnamed object that's in here. And so when that unique pointer goes out of scope, either through being unwound through a stack unwind, or it going out of scope, it will automatically call the destructor and clean up automatically after itself. Okay, so it's very powerful in that sense of it's trying to prevent memory leaks, okay? And we've got to really focus on this idea of ownership, okay? So unique pointer has exclusive ownership over unnamed object, okay? Let's take a look at it a little bit more. Again, we can create it this way, just for assignment, okay? Unique pointer x equals new int. We can't do the copy assignment like we showed you on a few slides earlier, but you can do this ownership transfer, okay? So unique pointer z is equal to standard move x. Transfers of ownership, z now owns that memory. X at this point is invalid, okay? So do not use for x object after you've done the standard move. Best case scenario, your code might still work. Worst case scenario, your code is completely going to go and do something completely random. The reason for that is after we call a standard move, it may or may not render the thing you moved from invalid, but what it does do is it's in an undefined state. And that idea of an undefined state means that you should not use the object after you've standard moved from it. And as you saw before, if you just call reset and don't pass anything in, it will delete the memory and just set it to a null pointer. Now, C++14 clears up this next bit and kind of prevents you from doing this next couple of lines of code, but C++11 allows you to do this situation whereabouts you can, through a whole lot of silly code, end up with two owners of a unique pointer. And I really stress, do not do this. Not even as a joke, don't do this. I can create a pointer to an int using new int and pass it in for arguments 1, so it is the brackets are missing from that line. I can then create a unique pointer, pass it in, that pointer to be the unique owner of. I can then create a second unique pointer. I'm not copying this assignment, and I don't have a copy assignment of the previous unique pointer, instead I'm copying in this raw pointer from up here. Now the problem is, because I've got P owning this pointer, or this heap object, I've got Q owning the same heap object, even though these are both unique pointers, when they go out of scope, that one piece of memory that was created will get deleted twice. Okay? So do not create two unique pointer objects to hold the same previously created heap object. It brings back the double free problem. And it violates the idea of things having exclusive ownership. Again, C++14 prevents you from doing this by having a thing called make unique. Okay? So that's C++14, but C++11, you still need to call the new, but you should do that by passing the argument in here, not creating on two separate lines like that. Yep.
Is there a way to check that at runtime?
Is there a way to check that at runtime?
Make sure it's not owned by something
unless you had a pool of weak pointers that you could check through or something like that, you cannot check that at runtime. It would be up to your code to be sensible to check. Well, not to check, but don't write code like this, is basically the short message. So you'll see the difference between these few lines here and this line up here. This line up here is very explicit of what you're trying to do. The lines before are very explicit about what you're trying to do. The difference here is you've created this named PI object, and you've passed the named object into the constructor for the unique pointer. Do you guys recognize the difference? I might have to pause here and highlight it again. This slide, we have one named object, which is the unique pointer UP, and the unnamed object UB stack. The next page, we have one named object being this in pointer, one named object, unnamed object being this new int up on the heap. We then have a second named object being this P here. Okay? Recognize the difference in the actual objects that you've got between these two slides. Previous slide, one named, one unnamed. Next slide. Before you get to the problem, you've already got two named objects and one unnamed object. Okay? Recognize the difference between those two slides. Okay, so that was unique pointers. I actually don't use unique pointers very often. I use shared pointers. Shared pointers have multiple owners. They're multiple pointers pointing to the same object in memory. And they're reference counted. So they get constructed, and when they get constructed, they'll go and create a piece of heap memory, and they've got the reference count being to 1. You create a second pointer to the same object, and reference count goes to 2. First shared pointer object goes out of scope, the reference count drops to 1. When all the shared pointer objects referencing the same piece of memory go out of scope, then that piece of shared memory gets destroyed. And the way in which you do this is you use a thing called standard make shared. Okay, so the previous slide we still had new. We didn't have delete, but we still had new. Okay, that's been replaced in C++ 14. Okay, but remember we're still C++ 11. C++ 11 though for shared pointer, create it through standard make shared. Okay, you don't want the word new anywhere around this. Okay, and so we can make shared. We can go into a second scoping brace here, create Q, copy constructor to P. This isn't going to do a deep copy, this is going to do a shallow copy. This is just going to copy the pointers. The object it's referencing is going to be a shared object at this point. When that second shared pointer, Q, goes out of scope, the reference count just drops back to 1. When the first shared pointer goes out of scope, the reference count drops to 0. And therefore the object gets deleted. And so there's a couple of things associated with these shared pointers. First of all, you've got two named shared pointer objects. You have one unnamed UB stack object, which is what those two shared pointers are sharing, are referencing. You also have a shared reference counter, one reference counter, which is being incremented or decremented as need be. Okay, so if you look at the examples here, this UB stack from a couple of weeks ago had a head pointer and then it pointed to the data. Okay, so these pointers, these shared pointers are both pointing to that shared pointer object, that shared piece of unnamed memory, and they've got a reference off to that shared counter, that shared reference counter. This is very similar to what we built manually on Thursday last week. Any questions about this so far? Okay, shared pointers are, for me, much more interesting than unique pointers are. So here we go. X is equal to standard make shared int. Okay, so that's going to go and create the int object on a heap and make a shared pointer to it. Y equals X, well, now both own the same piece of memory. Now let's talk about this reset. So on the unique pointer, when we called reset and went and deleted that piece of memory because there was only one owner. When we call x.reset, the memory is still going to exist. X.reset is going to reset the shared pointer x to a null pointer. But because y also has ownership over the thing it was previously referencing, it's not going to go and destroy that. It's just going to reference count down, so it's going to decrease the reference count, because y is still going to be referring to the same thing. If after calling x.reset we call y.reset, at this point now nothing is referencing that original piece of memory. Reference count goes to 0, therefore that unnamed object gets deleted. Okay? So a reference count is counting for ownership. Every copy of the same shared pointer owns the same pointer to object. And that's only freed when all the references are destroyed. Okay, makes sense so far? So let's talk about cycles. What happens in the situation that A has a shared pointer to B, and then B has a shared pointer to A? Now I've got one B object, one A object. A has a shared pointer to B. B has a shared pointer to A. Now maybe I've got another piece of code that also has a shared pointer to A. And what happens is A goes out of scope in that second piece of code. And you think that for object A has been destroyed, but hasn't. Because, remember it's referencing B, and then B also has a shared pointer back to it, so you've got this cycle going on. I probably should have a code example for this, I don't, unfortunately. Okay, but maybe I can just knock it up here on a text editor. Okay, let's talk about A. Okay, we've got object A. Okay, you're going to have to watch it up on the screen. Object A. And that's going to contain shared pointer to B. Okay? Object B contains shared pointer to A. Now, imagine that's a class declaration or something like that, okay? So inside I've got a function here called void foo. Okay? Got a void function here called void foo. Inside foo, I say something like auto p equals shared, make shared, but anyway, shared pointer to A. Okay, we're following so far? Say that A has a constructor which creates B, passes shared pointer to A, okay? It's pseudocode, so it doesn't quite work like this, but imagine I've got this set up, okay? A contains a shared pointer to B. B contains the shared pointer back to A, okay? Down here, I create P, auto P, inside the function foo, which is a shared pointer to A. So A goes and gets constructed, creates B, passes the shared reference back to itself. When P goes out of scope, what happens is this shared pointer, at this point, gets decreased, okay? Gets reference counter decreased. But because B is also sharing the same shared pointer, it doesn't get deleted. And so you've lost this reference off to these objects, but you've got a memory leak even with shared pointers. Everyone following how this is working? No? No? Okay, that's fine. The other example I can think of off the top of my head of how this might work is, let's talk about a graph. So assignment 3, you're going to be building a generic graph, okay? And a graph, you could construct it like this. A graph has a node, and the node class has a shared pointer to some edges, or particularly has a singular shared pointer to an edge object. The edge object stores a shared pointer back to its origin and its destination. Okay, think about that. So we've got a node stores edges, we've got an edge stores nodes. See that circular dependency there? If we go and delete the node, if we do not correctly delete the edges that are associated with it, what we think has happened is we think we've deleted the node, but we haven't. We've actually still got these circular shared references off to it. And it breaks. People look utterly confused. Who is confused? Can you let me know? Who's confused? Okay. Again, this week's tutorial is going to be looking at shared pointers, and in a minute we're going to be looking at weak pointers. Okay? Take a look at this week's tutorial when you get there and ask questions of your tutors about why we need these things called weak pointers. But let's just talk about, I suppose, ownership, or think about ownership of what's happening. Everything with a shared pointer, with a reference to a shared pointer, owns that object. Okay? So if you end up with cycles, if you end up with A owns B, B owns A, and you think that you've deleted A, B can still hold on to ownership of A, and you can lose reference to it and get a memory leak. It shouldn't be that complex, but it's probably a new idea to think about. Okay? If you're not following, it's okay. In the tutorials, hopefully you'll get a clearer idea. Again, maybe take a look at the textbook and bits and pieces like that. Okay? And then when we get to assignment 3, hopefully it'll become more clear. Otherwise, flick me questions. I might try and think over the next week about what maybe a clearer example is. Okay? But let's just settle for now. We've got this issue of cycles. Can we settle on that? Everyone's got this idea of this problem of cycles. So let's take a look at a weak pointer. Weak pointers are inherently related to shared pointers. You have something like this. A shared pointer called x, which is an int object. You then create a weak pointer by copying that shared pointer. But this weak pointer does not own the object in the same way that a shared pointer owns the object. Okay? So the weak pointer, you could think of being able to be pointed to the same object, but doesn't own it. Okay? Now, it doesn't quite work like that. I'm hand-waving a little bit. But you can think of a weak pointer as having a pointer to the object, but it doesn't own the object. And what that means is if the shared pointer gets deleted, or reference counted down to 0, the weak pointer still exists, but it's now going to potentially point to something that's been deleted. So we've got back to our problem of, oops, now we're referencing a piece of memory that's already been destroyed. What this means is a weak pointer cannot actually ever access the memory it's pointing to. Now this is going to really confuse everyone, because I've just told you, well, a weak pointer points to an object, but now I'm telling you, well, actually it can't actually get access to the data of that object. It can by converting itself up to a shared pointer. So let's work through this code. We create a shared pointer. We then create a weak pointer. We then promote this weak pointer to a shared pointer object by calling this thing called .lock. And .lock, what it does is it goes and it converts this weak pointer and returns the shared pointer to the memory that it should be pointing to. If that memory has been deleted, it returns a null pointer at this point. Now, there's another function you can call on the weak pointer, which is called, I just got to remember it off the top of my head. It's not called check, but it's called something like check. Let's go take a look. I had that before. It's called expired. So you've got this function on for weak pointer called expired. Returns true if the memory it's pointing to doesn't exist anymore. Turns false if it does, if the memory still exists. So you can check if this memory still exists. So you promote this weak pointer up to a shared pointer, and then you can do something with y. And then when that shared pointer gets destroyed, well, that one's still got the same reference count to it, so it's fine. Then x.resets, memory's deleted. So at this point, if shared pointer y and shared pointer x are both being destroyed, memory's been destroyed. Remember, we've still got this weak pointer WP over here, which is now pointing to destroyed memory. If we try to now get from memory it's actually pointing to by going wp.lock at that point, we get a null pointer. Okay, and then that next piece of code doesn't execute. So this is useful when you need to access a resource for a pointer that can outlive the resource. Again, talking about this week's tutorial, we have the idea of some courses and some students. The school object owns the courses and the students. The school object has a collection of shared pointer over course objects. The school also has a list of shared pointers over the student objects. Okay, we're clear on this bit so far. The student object has a weak pointer over the list of courses that it has. What this means is the school can go and delete a course object, and that course object will be deleted. If the student had a shared pointer to the course object, when the school goes and deletes the course object actually still exists. The only way to delete it would be the school would have to delete the course object and then have to go through all the student objects and delete their references to that course object. By the student object having a weak pointer to that to that course object, the school can go delete that course just in one call like that. And it doesn't have to worry about modifying the students. The students at some other point can realize, oh, my course has been cancelled. Okay? Again, that's actually this week's tutorial, but that's the way in which you can think about it. So think about that ownership. Who owns the object? It's possible to get access to a resource that you don't own. Now, the reason why that example wouldn't work with unique pointers is you could say, well, the school has a unique ownership over the course object. That's true, but then the student objects could actually never reference those course objects. So that's why you need to do it with a combination of shared pointers and unique pointers. Is that clear to anyone, or does that confuse people further? Who's getting this? Who's really, really, really confused at this point? Anyone really confused? Anyone a little bit confused? Okay. It's okay to be confused again. Look at the tutorials, okay? So here is how you might combine the weak pointers and the shared pointers. Okay, this code is going to be similar to what you had on the previous slide. You make a shared pointer called P. Okay, so P has a pointer to the unnamed object, has a reference count, it gets increased. You have a weak pointer down here. The weak pointer doesn't do anything to these things. Okay? So weak pointer kind of points off to these things, but realistically it doesn't. It just, I'm hand waving a little bit, but the weak pointer kind of just knows that these things are here, but doesn't really do much with them. It's not until you get to a shared pointer, Q equals P here, that pointer at that point now points to this unnamed object, and this reference counter gets increased. Okay? And again, for the rest of the slide, it's similar to what you've just seen with the objects being destroyed as they decrease. Okay? So let's talk about smart pointers for arrays. For an array, you can create a unique pointer over an array object. So you can create a unique shared pointer over an array, dynamic array. And when it goes out of scope, it gets deleted. Shared pointers do not support arrays by default. So you cannot have shared ownership over a dynamic array. You shouldn't be using arrays anyway. You should be using vectors or some other object, okay? But if you wanted to use a dynamic array, you can create a unique pointer over it. You cannot create a shared pointer over it by default. There is an alternative. You can create a thing called a deleter. A deleter is kind of like an overloaded destructor that you define how this thing goes and gets deleted. And so if you wanted to create a shared pointer over an array, you can pass in the deleter object, so the constructor of a shared pointer. And the deleter object, okay, this is actually a functor. The deleter object, or the deleter functor, goes and deletes like that. It's really bad style. Don't do this. Okay? You shouldn't be using old-fashioned arrays anyway, but if you are, do not go and create a shared point over them. Okay, it's messy. The reason why it's messy is defining a deleter functor, it starts to get really confusing about what your code's doing. Okay? C++ gives you lots of ways to do dumb things, and this is a very dumb thing to do. Okay, so we're clear about shared pointers, at least at the moment. Okay? Talking about shared pointers for 40 minutes is not going to get you into how they'll work. You have to get your hands dirty. You have to sit down and start coding some of these things. That's why, again, I keep on stressing this week's tutorial. Have a go at it before you get to class. Maybe, at least at the very minimum, have a look at the code. Try to understand why things are shared pointers and why they're unique pointers and so on and so forth. Okay, so I'm going to spend about the next 10 minutes just briefly talking over one, I suppose, final concept in C++ 11 that we haven't talked about so far, to do with constants. Okay, so this is actually unrelated to shared pointers, but it's just clearing up for 10 minutes. So at the start of this year, we talked about const, and we talked about the idea of things being const correct. And a const, or a constant, is a promise not to change the value of something. Okay? And it's used in defining functions, whereby we can safely pass to and from them with a promise not to change the internal state of an object. And the compiler enforces this promise being made. And assignment 2, some people are having issues in assignment 2 with the idea of const correctness, and particularly with the get Euclidean norm, because I've suggested that get Euclidean norm should be const, and yet at the same time I've told you, well, you should actually cache this result, and you're going, well, how can something be const, and I'm still trying to modify the internal state. And so we talked a few weeks ago about the idea of things being mutable. So if you're having that problem in assignment 2, you need to go look up at how the idea of mutable works. Because const recognises the logical state of something. It's a helper for us. It's a helper for us doing the right thing. Okay? Now, const expressions are related to const. And what they are is they're a way of creating functions or primary expressions that can be calculated at compile time. And it means that we can place some data into memory where it's unlikely to be corrupted, and we can improve performance. So const expression is a hint to the compiler to, at compile time, you can calculate the value of this function, and it will always stay the same. So a const expression is what we call a literal. A literal is like just the number 1 or 2 or 3. or 3.14. It can also be a const object, which is initialized from a const expression. So we've looked at const so far. So we can say const int max files equals 20. This 20 is a literal, and so this max files equals 20 is a const expression. And so at compile time, max files is given the value 20, and it always stays that way at compile time. Okay? The next line is still a const expression, max files plus 1. It's still a constant expression. At compile time, because this is constant over here, this gets hard-coded to be 21 at compile time. However, this next line without the word const here, so int staff size equals 27, is not at compile time compiled to be a fixed 27. That 27 actually gets assigned at runtime into your local stack memory, and that value can change. Okay? If we say something like const int sz equals get size, even though this is const on the left-hand side, get size, which might be down here, is not const because, well, this get size is reading from the keyboard. Okay? So a const expression is whereabouts the entire thing can be deduced at compile time. Why do we use this? Well, let's take a look at these next few slides. We had this max files of 20, that's fine. We had max files plus 1 being fine like that. We can do this. We can have a function called multiply, which takes in two values and returns for x times y of them. We can have this const int function, also this constant variable called val, equal multiply 10, 10. Okay, multiply 10 times 10. Now remember up on this previous slide, this call to this function get size didn't work because it was reading something from a keyboard at compile time, so at runtime. This multiply function, you'd expect off that previous slide to also run at runtime, not at compile time. But this const expr on the front of this is saying this thing, it just does something really simple. And so this is a hint or instruction to the compiler to say, at compile time, not at runtime, but at compile time, calculate out the result of this val. And so constant val will equal 100. It's const, it goes up into const memory. If we say constant z equals size, okay, so that's what we just saw, it only works if the size function is a constant expression. Okay. Again, be careful with pointers. First pointer here is a pointer to an int that's constant. Okay. The second line is a const pointer to an int. Okay, it's the same as moving around with the word const. Gets put there. So const expression functions are functions that can be used to calculate those values of const at that point. Okay? They are restricted pretty much to the idea of being literal types. So if we end up with a function down here of, say, new underscore sz, return 42, this can be a const expression function because it's returning a literal. Okay? So there's a special situation whereabouts you're trying to optimize your code, try and make it fast, and you've got something whereabouts at compile time you can deduce what the actual constant value should be at these points. Okay? I don't have any examples of these things running because they're not used that often, but they're a new C++ 11 optimization. At this point, I'm going to stop for 5 minutes, okay? This is the end of us talking about dynamic memory. This is the end of us talking about new and delete and exceptions and stuff like that. What we're going to be talking about for the next hour, but also then the next week and a half is templates, okay? So we're going to have quite a context shift in what we're talking about. So at this point, is there any questions though about what we've talked about with dynamic memory over the last week and a half?
What's about the constant expressions?
What about the constant expressions? Those are in there just for your information, okay? You can use them if you like. They won't be in the exam. I haven't used them so far. That's why I've only spent 10 minutes on them. They're just, if you have something that you might want to optimize, hey, it's a piece of C++11, it might be interesting. Okay? Any other questions? No? Okay, take 5 minutes. Okay, so let's resume. And so we're going to look at function templates. And function templates are what's going to lead us into talking more about assignment 3. So in thinking about function templates, let's talk about polymorphism. And so polymorphism, the idea of polymorphism is whereabouts you can have a type or types, and they can interact with each other, or they can take on different sort of behaviors. And so polymorphism comes in many different forms. Function overloading is a form of polymorphism. It's the same function, but behaving in different ways based on its parameters. Runtime polymorphism we haven't seen yet, but you would have seen it when you were working with Java. And you would have seen it in the idea of inheritance. So you might have talked, particularly if you're doing Java, you might have talked about the idea of a bank account and a check account. And a check account extends or inherits bank account. And so a check account does everything that a bank account does, but more. And so you can treat the check account object in the same way that you treat a bank account object. That's runtime polymorphism. We haven't done that in C++ yet. We'll do it in about week 11, okay? But there's different sorts of polymorphism. Templates are a form of polymorphism. They're polymorphic across unrelated types. And they're widely used inside libraries, in particular for STL, to achieve generality, flexibility, and efficiency. And so we've seen these templates already. We've used them already. We've created vectors of ints, vectors of floats. Templates are also a form of generic programming. Generic programming is about generalizing software components so they're independent of any particular type. We could create a generic add function, add two things together. We don't want to go and create one of those for double and int and float. We could create a generic template for a function called add that took in two types and added them together. And so function and class templates are the foundation of generic programming. And of course, the standard template library is a key example of it. And so we're going to spend some time in this lecture looking at function templates, and then we're going to lead into class templates. And assignment 3 is on class templates. So there's a whole list of things that we're going to look at in terms of function templates. Okay? This is what we're going to break things down into. I'm not going to read those all out because you can already see the headings. Now, the next couple of slides you would have also already seen. So this is just a bit of a rehash over what you've seen already a little bit of. Imagine that we have a function called min. And min returned the value that was minimum of two values that got passed into it. If I wanted to make this work across lots of different types, I might have to do some function overloading. I might have to create a min for int A and int B. But I can't pass the doubles into that because if I passed a double into that function there, what would happen is I would get the int version back of it. And so if I passed in 3.14 and 3.41, well, they'd both get converted to 3, and then I'd go, well, if min of 3 is free and wouldn't really work. So then I'd need to go create a double version to work on doubles. And function overloading would sort me out. But trying to write overloaded functions for every single possible type of number I could give min would be dumb and incredibly frustrating. The reason why it would be dumb is, once I had a new type come along, I'd have to write a whole new version of min just for that. And so you'd have problems. And so the idea of templates is to provide basically a recipe or a prescription for the compiler to automatically generate its own functions based on the type arguments coming in. And so they look like this at the top. Okay, and we've seen these slides already twice before. The word template goes at the start, type name, T. If you're coming from Java, we've talked about Java generics, and you would have seen E or something like that, same idea. This T is a substitute for some sort of type. And so template, type name T, returns a T, takes in two T's. Named variables A and B of type T return A less than B. In our code, we might write min 1.2, min 1.1, 2.2. The compiler uses these calls, uses this example here, to go and use this template prescription or template recipe to automatically create two functions, two overloaded functions, one for the ints and one for the doubles. Okay? So overloaded functions are generated at compile time based on the arguments of the functions that are calling them. We clear at this point? Yep. So if we break down what the function templates look like, they always have this bit at the top says template, and they'll say type name T, maybe comma, type name S, comma, type name E. Okay? You have one type name per type that you require. Okay? So this min function only has one type it requires because it's the minimum of a particular type of things. In assignment 3, when you're doing a graph, you'll end up with two type names. The reason why you'll end up with two type names, possibly N and E, okay, I'm highlighting it up on the screen here, is because you'll have two different types of data. You'll have the data that might be stored on the nodes and the data that might be stored on the edges as the edge weight. They could be two different types. So after the template, we can have multiple type names depending on how many types we need to know about. We then have the function prototype, what its return type is. Now, it doesn't have to be T. That could return an int. Maybe your function always returns an int. Maybe it returns void. Okay? But you've got your return type, the same as normal, which could be a named type or it could be the parameter type here. And then you pass in the arguments, which again, the substituted type T, or it could be a T there and an int there or whatever order you needed. If this type had type T and type S, maybe this one's T and maybe this one's S. It depends on what you're doing. So the interface is type dependent. The body is type independent. What that means is, see how inside this body here, we're referring to these named variables at this point. Okay? Now, we could create local versions of T and what other data types you needed, okay? But generally, this is type independent. Okay? So there's a separation of the type dependent and type independent parts of the functions. Okay? So T is a template type parameter. It's a placeholder for any built-in or user-defined type. Now, historically, so if you're looking up some old textbooks or some old code, instead of the word type name there, you might see the word class. Class is what used to be put into these things. When I learned C++ back in 2006 or something like that, I put class everywhere. Okay, that's changed. I don't know when it changed, but it's definitely changed to now be type name. Okay, because that going in there is not strictly a class; it could be a primitive type as well. Yep, up the back.
If you do choose to class
Yep.
and then pass in a primitive,
Yep.
what happens?
I'm assuming it works. So the question was, if you use class and pass in a primitive, does it work? I'm assuming it works. I don't know.
Yeah, it was made backwards compatible.
So it was made backwards compatible. Okay, yep. Yep. But don't put class there, put type name there. Okay? So we're going to look at an example about we're mixing type and non-type parameters. We have a template function here called findMin. And this is very similar to the min function that we just saw, only this is finding the minimum over an array. Okay, so before we had the min function, and it was just finding the minimum of 2 values. This is a min function that finds the minimum over an array. And so what we want to pass in to the template is the type of the array, which we don't know at this point. We don't know what the type's going to be. But we also want to pass in the size. And the size should always be an int or an unsigned int. Okay? The size of an array is always going to be an int. The size of an array is not going to be a double because that doesn't make sense. The size of an array is not going to be a string because that definitely doesn't make sense. Okay? So we can, in this template, give it the unknown type, and we can also give it a specific type it needs to know about. Then what you can do is you can say, okay, so this findMin returns a t, whatever type this is, takes in a const reference to an array of the size. Okay, so the square brackets here says size. Because remember, the size of an array needs to be known at compile time. And then what we can do is we can assign the first value in that array to be the min so far. We can just go into a for loop, and if this value is this and this value, set it, and it returns that particular value. That next part of the loop isn't that exciting. It's the generic type-independent way in which you might go through an array and find the minimum value. What is interesting is down in the main function down here. We have an array of ints and we have an array of doubles. The array of ints has 3 items. The array of doubles has 4 items. What happens here is when we say min of x, find min x like that on line 14, the compiler goes and creates us a version of findMin that takes in an int or an int array with the size 3. Okay, one function at this point. It takes in an int array size 3. The next line, findMin. Remember, this is an array of doubles, so this point size 4. Well, int array of size 3 doesn't work. So it goes and creates a new function called findMin, which takes in an array of doubles with size 4. And so what we say is for t is the type parameter, size is the size parameter. And notice that we're not, when we call findMin, using the angle braces to describe what those types need to be and what those sizing needs to be. The compiler automatically works it out based on what's being passed in as arguments here. Okay, so we're going to talk about template argument deduction in a few slides' time. But the compiler automatically works out what these types should be and generates us the right behavior. Okay, so this is what for code actually ends up looking like. Okay, so I just described to you this is what for code actually looks like. We create two versions of compiler, creates two versions of find min. One that's an int of size 3 and one that's a double. Basically what's happened is it's copied that code across and it's just substituted in for types and the size where required. Now, particularly with arrays, we have a problem with what's called code explosion. If we have many, many, many different types of arrays, all with different sizes, we get one function per different size of array. Okay? So that prescription, that template to how to generate a function, if we have lots and lots and lots of different ways of calling that function, we end up with lots and lots and lots of overloaded versions of that function. Okay? It's called code explosion. Okay? Not necessarily a bad thing, but it can cause problems. Okay? Not necessarily a bad thing. Let's take a look at this example. This example was the same template that we had before. Okay, so find min is exactly the same. What's changed is the main function. The main function here has an array of 3 ints. It has a const int sz size 3. And then we could say int y sz, okay? And that works because this is a constant expression. So generally, you cannot create an array by passing in a variable. Generally, the only way in which you can create an array is giving it an exact type and size, so exact size at compile time. This line 12 works because this int sz is const, and therefore this becomes a const expression, which we looked at very briefly a few minutes ago. And so that line 12 works. This wasn't const here. It's likely that actually the code would compile, and it is actually likely the code would run, but it's not strictly correct. Now, line 13, find min x. Remember that x is an int array, size 3. So it goes and creates a function, find min, takes an int, size 3. Y is an int array size 3. It's got no data on it, but an int array size 3. Because of that, that same find min that was generated in the previous line gets called. And so in this example, even though it's 2 calls to find min, only 1 is generated because the find min that's required is actually the same one in this situation. Okay? So expressions that evaluate to the same value are considered equivalent template arguments for non-type parameters. Okay? So the size, the non-type parameter, evaluated to the same thing. It works. So let's talk about how we compile these things. So we've stressed quite heavily the idea of separating your declarations from your definitions. Declarations go in the header file, definitions go in the .cpp file. The idea behind that is you can make your header file public. Everyone can go off and see your header file, but your private implementations of how things work deep within inside your class, they can go inside the .cpp file, and you don't need to distribute that. You can just compile that off to a .o file, and everything's happy. Problem with templates. Templates are prescriptions on how to generate things. Templates are not at compile time, so if you're compiling just a .o file, they're not actually compiled in the same way. They're only compiled when required. And so you need to put all your declarations and definitions into the header files for your code to go to work. Okay, so this is a change from what we've done up until this point. You should still only compile .cpp files though. Okay, so all the template declarations definitions go in for header files, but you only compile .cpp files. And so your CPP file, say user file 1.cpp, hash includes your min.h. User file 2.cpp, hash includes min.h. Min.h has the template definition for how this min function is templated and defined. What happens though is if you just compile this user file 1.cpp off to a .o file, that hash includes that, and then the second one off to a .o file, which includes that, and then you link them together, the first .o file and the second .o file actually have different instantiations of the same function. Okay, so this is at the compiler level, you've got different instantiations of the same function. The linker sorts you out. Okay? The linker will sort you out and sort out that problem. But you should be aware of this, okay? So, how we've been compiling up until this point is still how we'll probably continue to work, but the .h files need to have the definitions of the functions, not just for declarations, because these are prescriptions. What this means, though, is the implementation details are available in our .h file. So if we're trying to create some sort of top secret piece of code that nobody wants to see the implementation details of, well, too bad. Once it's in a template, it's available for everyone to see. Compiling the same template multiple times can also be quite slow. So you've got functions that hash include the same template file multiple times. Even with header guards, you can have problems. So let's talk about initialization of function templates. With compilers, and what we've seen so far is a compiler, what it does, it starts at the top of a file and works its way down and compiles each piece as it goes. And so a normal function declaration will get compiled when it gets defined. So when a function gets defined, normal function gets defined, it will be compiled at that point. But a template is not a normal function because it's only a prescription, a description or recipe for how something should be compiled. So a function template is not compiled when it gets defined. Not in the same way a normal function is, and this is why it needs to go in the .h file. If a function gets compiled and gets built when it gets first used. So if our compiler was coming through this piece of code here, it goes through the template, it stores off the information about how the template works, but it doesn't compile it. Okay, and again, on assignment 3, this is where you might have some problems. Actually, I'll talk about assignment 3 once I finish this slide. So let's talk about this. We have a template here, it doesn't get compiled at this point. When we hit the line standard cout min, at this point, it goes and creates the function that's required for this line of code to work. On the next line, we create a function pointer to that min function. When we create the function pointer to that min function, bang, the second version of it goes and gets compiled. Okay? Now, again, I told you at the start of the semester, don't use function pointers because they're a mess. They don't look very nice. But these functions get compiled when they are required. They don't get compiled just because the compiler sees a function template. It can't. If it tried to compile every possible version of that min it could be established when it first saw it, it would go and compile every single possible version of it, and it'll be horrible. Okay? So function templates are only instantiated when they're invoked or when their address is taken. So the address is this ampersand of the function up here, okay, for a function template. So points 1 and 2 on the slide are the points that whereabouts this template gets instantiated. Talking briefly about assignment 3. Assignment 3, you have 14 test cases. The reason why you have 14 test cases is you'll probably find that you'll pass the first couple of test cases, they'll compile fine. And then suddenly your .h file will not compile on some of the other later test cases. This is different to assignment 2, where that's assignment 2. Generally, if your .o file doesn't compile, it doesn't compile for all test cases because your .o file simply doesn't compile. So, standard non-templated classes, your file, your header, your .cpp file are either going to compile or not compile. Okay? Templated classes, and templated functions. You can have syntax errors in your templated functions. You can have bugs in your template functions that will cause them not to compile. But unless you go and instantiate them in a piece of code like that, that bug might exist for a long time because nobody's actually compiling against that particular recipe. Okay? So the compilation of how function templates work is different. What you can do is you can explicitly initiate your templates if you really wanted to. I've got an example of this with the giant caution of don't do this, okay? But if you really wanted to, say if you are writing some super secret code, you can just put your declaration up inside your .h file. Okay, so both on the left-hand side and on the right-hand side, I've got the same code. I apologize at how small that text is. It is quite hard to see. But in the .h file, I've only got the declaration of the template. I have the definition inside a .cpp file. And remember that definition still is only a prescription. It's only a recipe for how this function is defined. Still doesn't define it at that point. If I want to explicitly cause the generation of a particular version of that function, I can do that with these explicit initializations. Okay? Inside my main function, which hash includes min.h, okay, remember min.h does not define the prescription for how these functions are generated. Okay. What it does is it goes off and goes, oh, well, I can't work out how to compile these. That's okay. I can still compile to a .o file. Okay, I can still compile to a .o file. And the linker will sort me out. Okay, this is bad. Don't do it, but this is what's going to happen. So I'll actually compile these out for you. I have a make file over here. I'm going to do it one bit at a time. First thing I'm going to do is I'm going to make my min-instances.o file. Okay, so this might be similar to how we have our Euclidean vector.o file. Okay? That goes and compiles. And I now have min-instances.o. Min-instances.o, that object file, because min-instances.cpp had the recipe for how to generate the function, and had those two explicit instantiations I needed, it goes and works. If I now compile min user.o, it goes and compiles. Min user.o goes and compiles perfectly fine. It doesn't go and compile the min functions that we require because it doesn't actually have the templates, the definition of those templates, okay? But it's going to go and compile fine. And then when I make min user for dot executable, okay, it now goes and links those two things, and it works fine as well. And I can run that, okay? If I run that, I get the values out, okay? But this is all dependent on these explicit instantiations. If I go and comment these explicit instantiations out, like that, go and do that, and then I go and make, oops, that doesn't compile now. Well, actually, sorry, correction, it compiles. It compiled perfectly fine. Problem happened with the link. We know how linking works, right? Who doesn't know what linking works? How linking works? Anyone not know how linking works? Oh, a couple of people. Okay, let's back up. Okay, so compiling your code goes through a couple of stages. Okay? When you compile your code, it goes down and converts your code into, I'm hand waving a little bit, but some sort of machine level code. Okay, I'm hand waving a little bit. What it does is it reads through your code, it sees for hash includes, and when it sees hash include, it copies the entire contents of whatever you're hash including into your code at that point. Copies the entire thing in. And then reads through your code, line by line by line. What it does is if it sees a reference to a function call, okay, if it sees a reference to a function call, it doesn't, at that point, strictly check that that function call actually exists. It does in some instances, doesn't in some other instances, but it kind of puts into this machine code, oops, you need to call a function at this point, okay? And so it goes and creates these .o files, these object files, which says, okay, in this code, this piece of kind of hand-waving machine code, I need to call this function at this point, okay? And maybe this function is declared in some other .o file. Okay, it doesn't need at compile time to know that .o file, that function, how it works. What it does need to know is that's declared, and that's why we declare in the .h level. So the .h has for declarations. The compiler needs to know what these functions are declared. It doesn't need to know how they actually work. Okay, we're clear up to this point. People. Anyone lost at this point? No one following? Okay. So we've got these .o files. These .o files are compiled code in some hand-wavy pseudo-machine code type thing. And they know for functions that should be called. They know that for declarations of a functions are floating about, but they might not know for actual implementation of how these things work. The linker goes and gets all the .o files and plugs them all together into one final executable. And to do that, for linker creates, I'm not much of a compiler's guy, so I'm hand-waving a lot, but basically creates some lookup tables. And so when it sees the function call, it looks up in the table how that actually needs to work and what exactly in the machine level code needs to happen for that function to be called. And so the linker plugs these function prototype declarations to get it into the actual implementations of how they work. That is how, in assignment 2, our Euclidean vector.o gets linked against, say, our Euclidean vector tester.o file. Okay, separate compilation, they get linked together. And so what's going on in this example, remember we've got a couple of stages of compiling that goes on here. We want to compile min_instances.cpp file. We want to compile a min_user.cpp file. And then we want to link everything together. So if I make the min_instances.o, it will make. Bang, works. The reason for that is min_instances.cpp actually doesn't contain anything. The reason why it doesn't contain anything is it's got the template, but remember I took out the explicit instantiations. Okay, so it's saying, well, here's a recipe, but I don't actually require anything. I hash include min.h. Okay, so I've got min.h. So all that the min_instances.o file knows about is there's a function called min, but it doesn't really care. The min_user file, what it does is it needs to know about this function called min. And min.h declares that function called min.h. And so this will compile fine. Make min_user.o. Remember, this is the .o file, it's the compilation stage. Okay? Compiles fine. But remember now I have a min_instances.o that actually just knows about this min function but doesn't actually define how it works. And min_user has a main function which is fully defined and also has a declaration of min that it's looking for. Two of them, in fact. It's got one for ints and one for doubles. But it doesn't know the definition of them. So when I try to link these things together, remember I've deliberately taken out this definition of how these things work. This is the point I get this undefined reference. Okay, because this undefined reference is saying, I have a reference to something, I've got a declared reference to this function prototype, but it's undefined. I haven't defined how it works. That's the problem. Okay, we clear? Yep. I'm going to back up real quick. I put these explicit instantiations back in to mininstances.cpp. Okay? Put those back into mininstances.cpp. Okay, so inside mininstances.cpp, I'm now going to create mininstances.o. Okay? And when I create mininstances.o, it is now going to contain two definitions of that min function because of the explicit instantiation. So before, mininstances.o didn't actually really contain anything other than a reference to this templated type. Now it's going to have two definitions. Okay, so mininstances.o, bang, it compiles. I'm not going to recompile min-user.o because min-user.o hasn't changed. Min-user.o, remember, it needed to know about min, and it already knew about that because of the .h file. It didn't need to know how they're defined. But now, because min instances has got the definition of these two functions inside it, when I do the link, so when I link those two files together, bang, it works. And now when I run it, hey, it runs. Okay? Who's confused? Anyone confused? Is this more clear to the guys who were confused before? Yep. Okay, so one other thing I'll quickly show you. And this is why this whole way of doing min instances is dumb. Okay? If I get rid of min instances entirely, and inside min.h, give the definition of that recipe at this point. And then call make min user. By the way, most people, who doesn't know how to properly use a make file here? Everyone knows what make files do, right? So if I just go and run make min user again, it will go and recompile for the things that I've changed. Okay? So I've changed min instances.cpp, and I've changed min.h. Because I've changed the min.h file, everything's going to have to recompile. But what I've done is I've moved the definition of that template from the .cpp file up to the .h file. I have completely got rid of the explicit instantiations. Completely got rid of the explicit instantiations. So they need to now be worked out by this main function here. This will compile. Oops, it's gone off the screen, but it compiled fine. No issues. And I run that, and it runs fine. Okay, so this is separate compilation. I have the compilation of the code into object files. I then link the object files together into a final thing. Okay? Question? Yep.
What happens if you were to put in integer and double?
Whereabouts?
Say min 1 and min 1.
Oh, easy. Well, let's try it. What happens? I think I know what happens, but let's take a look. Actually, no, correction. I know what's going to happen. It's not going to compile. Okay, so this isn't going to work. Now, it's funny that this isn't going to work because if this was just a standard overloaded function, it would work. The 1 would get automatically promoted to 1.2. Automatically promoted to 1.2. This isn't going to work, and the error that you're going to get is going to say it needs 2 arguments. Bang, there you go. So, okay, no matching function call for int double. The candidate is T, AB. Template argument deduction substitution failed. Deduce conflicting types, int double. Okay, can't work it out. Okay? The easy way of fixing this is like this. Let me think. Actually, there's no easy way of fixing this particular example, to tell you the truth. My easy fix for this example was going to be this. Type name, u, pass in u. Okay, that was going to be my easy fix for this example. Anyone got any idea what the problem with this fix is? By the way, this will compile and run. But is there a problem with my template now?
You don't know which type you're going to be returning, which like U might be the min, and then you're going to be returning it as type T.
Yeah, so I'm always returning type T. And so the first one will behave as expected. The second one, you don't know what's going to happen. So here, in this case, it's returned 1. But let's just say here that I pass it in, instead of 1, that I pass it in 0.2. So I've got 1 and 0.2 I want to get from min of those values. Okay, compile that. Instead, I'm just going to get 0 because it's going to have typecast that double down to there. Okay? So we're going to talk about how all this works. We're not going to get through it all today, but we're going to talk about how these type situations occur, and even how, particularly with C++11, we could use... Actually, I'll show you now. I'm going to show you something really cool, given I'm running out of time, so I'm going to have to shift a whole ton of stuff to Thursday. How we fix this in C++11 is we use what's called a trailing return type. Okay? This is the point about I stuff up and it doesn't work, but let's see. Decal type. Let me think about that. Can I do that? That's not going to work. Let me try this one. This may or may not work. This is a risk. Oh, how cool is that? Wow. I'm not joking, I was not expecting that to work myself. Okay? I cannot believe that works. That's how cool C++11 is. So, what I've done, is probably as confused as you guys are, is I've created this template. I've put the word auto in front of the function min. And so auto, as we've seen with variables, is automatically work out what the type is at compile time. The trailing return type, you've probably seen very briefly in Lambda functions last week. Okay? The trailing return type says, actually, I can't work out what the type is beforehand, so at some other point, I'm going to tell you what the return type is. Decal type is a new C++11 thing that allows you to declare, or it to work out automatically what the type is going to be. And just to prove that this works completely, let's go back to change it to 1.2 and make that, and run that, and bang, I've got an int out this time. Okay? So what this decal type does, I'm going massively off script right now, but what this decal type does, it says, at compile time, sort of work out what the type of this thing could be as a result of this expression. So the expression I've got there is a less than b, question mark a colon b. Okay, work out what this is. Because this is a const expression, it can work it out. And that's going to be the return type of this function. It's pretty cool. Who likes it? Most people. Who is confused? Anyone? I'm myself quite amazed that that works. Do I have some questions? Yeah.
If you don't have decal type, will the auto just die like the previous examples?
Okay, so if I don't have decal type, if I get rid of that entirely, let me do that.
Will the auto be smart enough to figure it out, or it'll just...
Yeah, hold on. I misunderstand what you're trying to ask. So if I get rid of that entirely and try to compile that, is that what you're saying?
Yeah.
Yep. I'll get an error. Okay, so error min function uses auto without return type. Okay, that's probably gone off the slide. Without trailing return type. Okay? Deduced return type is only available with C++1y. What this means, okay, if I really want to be a smartass, there's yet another version of C++ coming out. It's called well, 14 is out, 17 is coming at some point. If I change all these C++ 11s to C++ 17s, okay, so this is going way off script again. Why isn't this working? Replace all in document. Save. Okay, let's see if this works. It didn't like me. It didn't recognize C++ 7, so I was trying to change it to Y. Bang. There you go. So C++ 17, you can forget about a decal type entirely. Okay? Don't do this because we're definitely not compiling your code against something that's not for standard at the moment. I had about 2 questions up that way. Yeah.
What happens if you pass in two, like, completely different types, like an int and a string, or a class of one type and a class of a different type?
Okay, so what happens if we pass it in an int and a string? It's not going to compile because we need to do the comparison of a less than operator. Okay, so all these things are using the less than operator comparison. And an int and a string is not going to have a less than operator comparison defined for it. We can pass it in anything that does have a less than operator defined for it. So if we had, say, it'd be a dumb thing to do, but I could actually go and, definitely not going to do it with 3 minutes until the lecture recording cuts off, but I could definitely go and create my own string wrapper class that overloaded the less than operator to compare it to an int. And I used s to I or something like that to convert that string to an int. Hey, that would work fine.
So that would throw a runtime error.
No. If I did it now, it would return a compile time error.
If you were like reading from a file or something and didn't know what input it was going to get.
Yeah, it's going to throw a runtime exception. Yeah. I have one more. Yep.
Does this mean that it's generating 2 function definitions? So when you use def type
Yep.
for the compile to return what return type should be,
Yep.
and you had one where you wanted to return an int and one instance where you return a double,
Yep.
you then have 2 different
I don't think so. Okay, I'm not 100% sure myself, but I don't think you would have ended up with 2 of them because it comes back to the fact that this min user.cpp, remember this is a const expression, so at compile time we know the values of what this thing's going to be, and so it works out. I don't know what would happen if you didn't know that. Maybe you do get 2. I honestly don't know. It might be something to play with and figure out. Okay, so we've gone through the explicit instantiations. One additional thing we can finally note is if we put the word extern in front of that explicit instantiation, it won't actually instantiate it. It will assume that it's been generated somewhere else. Okay? Okay, so at this point I'm going to stop because we're out of time, and also with that example we've gone a little bit off track, but that's okay, that's cool. On Thursday, we're going to continue to look at how these template arguments are deduced, which should hopefully clear up some of those questions from today. And then we'll look at class templates. Any other questions right now? No? Okay, we're done.